Welcome to the Deep Dive, where we unlock the hidden truths within the information you share with us. Today, we're diving into a bit of a molecular mystery.
Oh, what's that?
Why do some chemical reactions happen like that instantly, while others just sort of grind to a halt or maybe even fail entirely?
That's a great question. And the answer, well, it often lies not just in what atoms are there,
Right.
but how they dance and twist and turn in 3 dimensions. It's all about the shape.
Exactly, that dynamic movement.
Precisely. We're venturing into the world of conformational analysis, and we're drawing heavily today from Chapter 16 of Clayden, Greaves, and Warren's Organic Chemistry, the second edition. It's a fantastic resource for this.
Okay, so our mission today is to really understand these um, molecular gymnastics, how molecules twist, what energy barriers they face.
And why these constantly shifting shapes are so profoundly crucial. I mean, for understanding everything from how a drug works to, how basic biological processes actually happen.
Get ready for some genuine insights, everyone, because this stuff, it really underpins so much of chemistry.
It truly does.
So when we talk about molecular shape, let's just nail this down. What exactly are we getting at? And how is this conformational analysis different from what, we might already know about stereoisomers?
That's that's a really crucial starting point. The distinction here is between conformation and configuration. They sound similar, but they're fundamentally different concepts.
Okay, unpack that for us, configuration first.
Right. Configuration refers to different compounds altogether, or, different stereoisomers that can only be interconverted by breaking bonds and then reforming them.
Okay, breaking bonds is the key.
Exactly. Think of E and Z isomers around a double bond. You can't just twist one into the other.
Right, you'd have to break that pi bond.
Precisely. So they're fixed in their arrangement relative to each other, different molecules.
So configuration implies a permanent, sort of rigid structural difference.
Okay. So how much freedom, then, do molecules actually have to change their shape without breaking any bonds?
Well, that's where conformation comes in. Conformations describe different shapes of the same compound.
The same molecule, just different poses.
Exactly. Interconverted simply by rotation around single bonds. No bonds broken at all. Think of it like a dancer shifting poses. It's still the same dancer, just a different arrangement.
Like that pea moth pheromone example from the source material. It can twist into lots of shapes, but it's still the same chemical.
That's a perfect illustration. It highlights this dynamic nature.
So this molecular dance,
Hmm.
does that mean if these single bond rotations happen really fast, our camera, like an NMR machine, just sees an average, like a blur?
You've got it. The rate of this twisting is tied directly to the energy barrier for that rotation.
Oh, okay.
So taking amides, like DMF. The barrier to rotating around that CN bond is about 80 kilojoules per mole.
Which is fairly high for what looks like a single bond. It is, because of the partial double bond character, and it's high enough that at room temperature, an NMR spectrum can sometimes actually show distinct signals for groups on either side of that bond. The rotation isn't fast enough to average them out completely. Now compare that to a real double bond, like in but2. The barrier there is enormous, 260 kilojoules per mole.
Wow.
Yeah, that completely prevents rotation. And that's why E and Z isomers are separable. They're distinct compounds because you can't just twist between them.
So for our NMR camera, what's the threshold? What's too fast to tell these shapes apart?
Well, generally speaking, if the interconversion is faster than about, 1,000 times a second, roughly 10 to the 3 per second, an NMR machine will average the signals.
Okay.
For something like cyclohexane at room temperature, the rate of ring flipping, which we'll get to, is around 2 times 10 to the 5 per second.
Way faster.
Way faster. So the NMR just sees an average proton signal. But, and this is key, if you cool it down.
You slow the dance?
Exactly. You slow the motion down enough below that threshold, and suddenly you can see the individual signals for the different types of protons.
Fascinating. Okay, to really grasp this dynamic world, let's start simple, like really simple. What about ethane? What can that tell us?
Ethane is the perfect starting point. Simplest molecule with a carbon-carbon single bond. And it basically exists in two extreme conformations when you look down that CC bond.
Right, using those Newman projections.
Yeah.
Where you look straight down the bond axis.
Precisely. You've got the staggered form. That's where the CH bonds on the front carbon are positioned exactly halfway between the CH bonds on the back carbon, maximally separated.
Okay, sounds stable.
It is. That's the lower energy form. Then you have the eclipsed form. That's where the CH bonds on the front and back carbons are directly aligned, lined up perfectly.
And that sounds less stable, more crowded.
Exactly. It's higher in energy than the staggered form by about 12 kilojoules per mole. And importantly, the eclipsed conformation isn't really a stable form where the molecule hangs out. It's an energy
It's
maximum.
transition state.
Precisely. It's the peak the molecule has to climb over as it rotates from one staggered conformation to another.
Okay, but why is eclipse higher in energy? Is it just electron clouds bumping into each other?
That's part of it, yeah. There's electron repulsion between those aligned bonds, sort of a subtle steric effect. But there's another factor, arguably more significant according to modern understanding.
Oh.
It's about orbital interactions. In the staggered conformation, there's a stabilizing interaction where electrons in a CH bonding orbital on one carbon can sort of delocalize slightly into an empty CH antibonding orbital, the sigma star orbital on the adjacent carbon.
Like electrons finding a little extra space to spread out.
Exactly. It's called hyperconjugation.
Right.
And this stabilizes the staggered form. In the eclipsed form, those orbitals don't line up properly for this interaction, so you lose that stabilization and you have the repulsion.
Ah, okay. So it's both repulsion and missing out on stabilization. Makes sense. What about propane? Adding another carbon, does it just follow the same pattern?
The very similar pattern, yes. You still have staggered and eclipsed forms as you rotate around the CC bonds. The rotational barrier is slightly higher, about 14 kilojoules per mole instead of 12.
Why slightly higher?
Well, now you have a methyl group eclipsing a hydrogen, which is slightly worse than just two hydrogens eclipsing, but it's still mostly about that electron repulsion and orbital overlap effect. The energy profile looks basically the same, just a slightly higher peak.
Okay, so ethane and propane are pretty straightforward.
Yeah.
But here's where, as the source says, it gets really interesting. Butane. Now we're replacing hydrogens with larger methyl groups. What changes?
This is where things get significantly more complex. Because with butane, rotating around that central C2-C3 bond means not all staggered conformations are energetically equal anymore, and neither are all eclipsed conformations.
Because the methyl groups are bulkier than hydrogens.
Exactly. They
Okay.
take up more space. So let's look down that central bond using a Newman projection. The most stable form, the lowest energy conformation, is the anti-paraplanar staggered conformation.
Anti means opposite.
Right. The two methyl groups are 180 degrees apart, as far away from each other as possible, maximum elbow room.
Okay, that's the global minimum. What else?
Then there are two other staggered conformations called synclinal, or more commonly, gauche.
Gauche. Like awkward.
Maybe a little. In the gauche forms, the methyl groups are only 60 degrees apart. They're still staggered relative to hydrogens, but the methyl groups themselves are much closer than in the antiform.
So they bump into each other a bit. Steric hindrance.
A little bit, yes, there's some steric repulsion. So the gauche conformations are slightly higher in energy than the antiform. They're local energy minima. And there are two of them, mirror images of each other.
Okay, anti is best. Gauche is okay, but a bit crowded. What about the eclipsed forms? Are they worse?
Oh, yes. Much worse. The absolute highest energy point is the syn-paraplanar eclipsed conformation. That's where the two bulky methyl groups are directly eclipsing each other, 0 degrees apart.
That sounds really unstable.
It is. Very high energy due to severe steric clash. Then there's another type of eclipsed conformation, the anticlinal form, where a methyl group eclipses a hydrogen. That's still high energy, higher than any staggered form, but not quite as bad as the methyl eclipse.
So for butane, steric repulsion becomes a really major factor in determining the relative energies.
Absolutely. You have the antiform as the most stable overall. The two gauche forms are also stable conformers, just slightly less so. These stable, low-energy shapes are what we call conformers.
And the molecule is constantly flipping between these.
Rapidly interconverting at room temperature, yeah. It spends most of its time in the anti- and gauche wells, quickly passing over those high-energy eclipsed barriers, like that energetic dancer finding the most comfortable poses.
Okay, that gives us a good picture for open chains. But let's switch gears. Let's talk about rings. My brain always pictures them as flat, like hexagons on paper. But the source makes it very clear that's usually wrong. What's going on there?
You're absolutely right. The assumption of planarity is often incorrect and can lead you astray. Cyclic compounds experience strain.
Strain, like tension.
Exactly. And it comes from a couple of main sources. First, there's angle strain. This happens when the bond angles inside the ring are forced to deviate significantly from the ideal tetrahedral angle, which is about 109.5 degrees for sp3 carbons.
Like in cyclopropane. A triangle.
Perfect example. Cyclopropane forces those CCC bond angles to be 60 degrees. That's a huge deviation from 109.5, so it's under immense angle strain.
Wow. Okay, angle strain. What else?
The other major factor is eclipsing strain, or torsional strain. This is exactly what we saw in eclipsed ethane. If the ring forces CH bonds on adjacent carbons to be aligned, you get that high-energy eclipsing interaction.
So rings have to worry about both bad angles and bonds lining up.
Precisely. And they often contort themselves into non-planar shapes to try and minimize both types of strain simultaneously.
The source mentioned using heats of combustion to actually measure this strain. How does that work?
It's a clever empirical method. You basically burn the cycloalkane and measure the heat released per CH group. Then you compare that value to the heat released per CH group in a long, flexible, linear alkane, which is considered essentially strain-free.
And the difference tells you the strain in the ring.
Exactly. The excess energy released by the strained ring corresponds to the amount of strain energy it contained.
So what did this reveal about different ring sizes?
Some really fascinating trends. Cyclopropane, the three-membered ring, as we suspected, has enormous strain, tons of angle strain, and all its CH bonds are fully eclipsed. It's got nowhere to hide.
Double whammy.
Big time. Then cyclobutane, the four-membered ring, if it were flat, the angles would be 90 degrees, still strained, but it also would have lots of eclipsing. So what does it do? It puckers. It adopts a sort of folded or butterfly shape.
What pucker?
Puckering slightly worsens the angle strain, but it significantly reduces the eclipsing strain. So it's a trade-off. It finds a compromise to lower the overall energy.
Okay. Encyclopentane.
Yeah.
5 members. That sounds like it should be close to the ideal angle if flat.
If it were a flat pentagon, the angles would be 108 degrees, which is very close to 109.5. Minimal angle strain.
But all the hydrogens would be eclipsed.
Exactly. So cyclopentane also avoids planarity. It distorts into what's often called an envelope conformation, where one carbon is puckered out of the plane of the other four. This relieves most of the eclipsing strain, even though it introduces a tiny bit of angle strain. Again, a compromise.
So it seems like avoiding eclipsing strain is often a major driving force, even if it means slightly worse angles.
That's a very good observation. Torsional strain seems to be particularly unfavorable.
And then cyclohexane. 6 members. What did the heat of combustion show for that?
This is the star. Remarkably, cyclohexane is essentially strain-free. Its heat of combustion per CH group is almost identical to a linear alkane.
Wow. How does it manage that?
Through its preferred shape, the famous chair conformation.
Ah, the beach chair.
That's the one. In the chair conformation, all the bond angles are perfect tetrahedral angles, 109.5 degrees, so zero angle strain.
Okay.
And crucially, if you look down any CC bond in the chair using a Newman projection, all the CH bonds and CC bonds are perfectly staggered.
So no eclipsing strain either.
None at all. It's a masterpiece of strain avoidance. It hits the sweet spot, minimizing both angle and torsional strain simultaneously.
That's really elegant. And the source, I remember, has really good diagrams and tips for drawing these chairs properly, which is super helpful. It's tricky to get right on paper.
It takes practice, definitely. But visualizing it is key, and within that chair, the hydrogens occupy two distinct types of positions.
Right, axial and equatorial.
Exactly. Axial hydrogens point straight up or straight down, sort of parallel to an imaginary axis running through the center of the ring.
Like flagpoles.
Good analogy. And equatorial hydrogens point out sideways, roughly around the equator of the ring. Each carbon has one axial bond and one equatorial bond. And as you go around the ring, the axial bonds alternate. Up, down, up, down. Same for equatorial.
Okay. What about other shapes for cyclohexane? I remember reading about a boat form. Is that also strain-free?
The boat conformation is also free of angle strain. All the angles are still 109.5. But
It must have eclipsing strain.
severe eclipsing strain. If you look down the sides of the boat, the CH bonds are eclipsed. And worse, the two hydrogens pointing inwards at the bow and stern of the boat, the flagstaff hydrogens, get very close to each other.
Bump heads, like you said.
Exactly. That flagpole interaction makes the boat conformation significantly higher in energy than the chair, about 25 kilojoules per mole higher.
So not a place the molecule wants to be for long.
Definitely not. However, the boat can twist slightly to alleviate some of that strain, particularly the flagpole interaction. This forms the twist boat conformation.
Is that stable?
It's a local energy minimum, yes. It's about 4 kilojoules per mole, lower in energy than the true boat, but still much higher than the chair. So the chair is the undisputed champion, the global energy minimum. The twist boat is a genuine conformer, but much less populated.
So the chair reigns supreme. But do molecules get stuck in one chair form, or can they flip between them?
Oh, they flip. Cyclohexane undergoes rapid ring inversion or chair flip at room temperature. It's constantly happening.
What happens during the flip?
Everything swaps. All the bonds that were axial become equatorial, and all the bonds that were equatorial become axial. The whole ring turns itself sort of inside out.
How does it do that? What's the path?
It's not a direct chair-to-chair jump. It goes through a sequence of higher energy shapes. It goes from chair up to a high-energy half-chair transition state,
Okay.
then down slightly into that Twist boat minimum we just talked about.
Ah, the Twist boat is an intermediate.
Exactly. Then it goes up again through another half-chair transition state, and finally down into the inverted chair conformation.
Wow, that's quite a journey. Is there much of an energy barrier?
Yes, the main energy barrier, the highest point, is the half-chair transition state, and the total barrier for the chair-to-chair interconversion is about 43 kilojoules per mole.
And at room temperature, that barrier is overcome rapidly,
Very rapidly, about 200,000 times per second, as we mentioned earlier.
which explains the NMR. At room temp, the flipping is so fast, the NMR just sees an average signal for all the protons. It can't distinguish axial from equatorial.
Precisely. The shutter speed of the NMR is too slow to catch the individual conformers.
But if you cool it down,
You slow the flip right down, below that NMR timescale, and then, poof, you see two distinct signals. One for the axial protons and one for the equatorial protons. It's beautiful experimental confirmation of this dynamic process.
it really is. It shows these aren't just drawings, they're real moving structures.
Huh.
Okay, so what happens if we complicate things? What if we add a substituent, like a methyl group, onto the cyclohexane ring? Does it care if it's axial or equatorial?
Oh, it cares a lot. In almost all cases, the conformer where the substituent is in the equatorial position is preferred. It's lower in energy.
Why? What's wrong with being axial?
The problem is something called 1-3 diaxial interactions. An axial substituent bumps into the two axial hydrogens located 2 carbons away on the same side of the ring.
So if you imagine the chair, an axial group pointing up will clash with the other 2 axial groups pointing up on the same face of the ring.
Exactly. It's a steric clash, like trying to fit 3 bulky items into the same small space.
Like having a big water bottle sticking straight up in your backpack, constantly bumping against your shoulder blades.
That's a great analogy. It's uncomfortable for the molecule. For methylcyclohexane, putting the methyl group equatorial avoids this clash, and the energy difference is significant. The equatorial conformer is about 7.3 kilojoules per mole more stable.
7.3. What does that mean in terms of population? How much is equatorial versus axial?
At room temperature, that energy difference translates to about a 20.1 ratio.
Oh.
So about 95% of the molecules will have the methyl group equatorial at any given moment.
Wow, a strong preference. And presumably, the bigger the group, the stronger the preference.
Finally, yes. The steric clash gets worse with bulkier groups. The source shows a table, and it's quite dramatic. Take a tert-butyl group that's C bulky. It's very bulky.
Huge.
Its preference for the equatorial position is enormous. The energy difference is over 20 kilojoules per mole, leading to an equilibrium ratio of more than 3,000.1 favoring equatorial.
3,000 to 1. So it's basically always equatorial.
Pretty much. The energy cost of putting a T-butyl group axial is so high that the molecule essentially refuses to do it.
Right.
We call the T-butyl group a conformationally locking group. It locks the ring into the conformation where it's equatorial.
That's a powerful effect.
Right.
But you said generally bigger is worse. Are there exceptions or nuances?
There are. What's interesting is comparing methyl, ethyl, and isopropyl groups. Ethyl and isopropyl are technically larger than methyl, but their preference for the equatorial position isn't dramatically larger than methyl's. The energy differences are quite similar, actually,
Why is that?
because ethyl and isopropyl groups can rotate around their bond to the ring. They can orient themselves so that a smaller hydrogen atom points towards those axial hydrogens, minimizing the clash.
Ah, they can tuck themselves in a bit.
Exactly. But the tert-butyl group can't do that. No matter how it rotates, it's forced to point one of its bulky methyl groups directly at the axial hydrogens. That's why the penalty is so severe for T-butyl.
Okay, that makes sense. It's about the closest approach.
Precisely. And here's another interesting one. A methoxy group, OCS. Oxygen is bigger than carbon, so you might expect it to have a stronger equatorial preference than methyl.
Yeah, sounds logical.
But it actually has less preference. The equatorial form is only about 2.5 kilojmol more stable
Huh.
because the oxygen atom acts like a spacer. The CO bond is longer than a CC bond, and the methyl group is attached to the oxygen, not directly to the ring. This moves the bulky methyl part slightly further away from those troublesome axial hydrogens.
So the oxygen atom cushions the blow, so to speak.
You could think of it that way. It highlights that it's not just raw size, but the specific geometry and bond lengths that dictate the strength of these 1-ferrous-3 diaxial interactions.
Fascinating subtleties. Okay, what if you have two substituents? How do things play out then? Say, a cis or trans dissubstituted cyclohexane.
Now you're adding stereochemistry into the mix, cis and trans isomers. And you have to consider the conformational preferences for both groups. Let's take 1-ferrous-4 dissubstituted cyclohexane as an example.
Okay.
Consider trans 1-ferrous-4 cyclohexanediol. Trans means the two OH groups are on opposite sides of the ring. In one-chair conformation, both OH groups could be axial.
Sounds unstable. Double 1-ferrous-3 diaxial interactions.
Very unstable. But if the ring flips...
Then both OH groups become equatorial.
Exactly. And the diquatorial conformer is vastly more stable. So trans 114 dissubstituted compounds strongly prefer the conformation where both groups are equatorial.
Makes sense. What about the cis isomer? Cis 144 cyclohexanediol.
Cis means the groups are on the same side. So if you draw the chair, one group must be axial and the other must be equatorial.
You can't have both equatorial or both axial in the cis 1,4 case.
Nope. And when the ring flips, the one that was axial becomes equatorial and the one that was equatorial becomes axial. So both chair conformers have one axial and one equatorial group. The energy difference between them will depend on which group is bigger, but you can't avoid having one axial substituent.
Okay. What about 173 dissubstituted?
That's different again. For cis 1,3 dissubstituted, both groups can actually be equatorial in the same chair conformation. Or if it flips, both become axial.
So cis 1,3 strongly prefers the diquatorial form.
Absolutely. Whereas trans 1,3 dissubstituted will always have one axial and one equatorial, similar to cis 1,4,4.
Wow. Okay, so you really have to consider the substitution pattern, 1,2, 1,3, or 1,4, the stereochemistry, cis or trans, and the chair flip to figure out the most stable arrangement. It's like a multi-dimensional puzzle.
It really is. And understanding these preferences is crucial, especially when you get to more complex systems where ring flipping might be restricted, like with those locking groups, or infused ring systems.
And decalins, two fused rings.
Exactly. Decalins are two cyclohexane rings fused together. There's transdecalin, where the rings are fused via two equatorial bonds relative to the junction. And there's cisdecalin, fused axial equatorial. Cisdecalin can undergo a ring flip, although it's somewhat restricted. But transdecalin is conformationally rigid. It cannot ring flip.
Why not?
Because flipping it would require forcing the ring junction into an impossible diaxial arrangement for a six-membered ring. The geometry just doesn't work, so transdecalin is locked.
Locked in shape. And steroids. They're built from fused rings too, right?
They are. Steroids typically have a core of 3 cyclohexane rings and 1 cyclopentane ring, all fused together. Usually the ring junctions are trans, except sometimes between the first two rings, A and B.
So like transdecalin, they're rigid.
Largely, yes. Because of these multiple fused, generally trans junctions, the whole steroid backbone is conformationally quite rigid and cannot undergo chair flips.
And that must be critical for their biological function.
Absolutely critical. It means any substituents on the steroid skeleton are held rigidly in either an axial or equatorial position. That precise 3D shape is essential for how they interact with enzymes and receptors in the body.
It's amazing how these structural details lock molecules into specific shapes, with such profound consequences. And you mentioned earlier, figuring this out for steroids is what led Sir Derek Barton to develop conformational analysis and win a Nobel Prize.
That's right. It came directly from trying to understand the reactivity differences between axial and equatorial groups in steroids. It wasn't just abstract theory, it solved real chemical problems.
Which brings us perfectly to the final piece. What does all this mean for reactions? Does a molecule's preferred shape actually impact how it reacts?
Absolutely. Critically, the conformational principles we've discussed are essential for understanding reactivity. Let's take the SN2 reaction, a classic reaction everyone learns.
Right, bimolecular nucleophilic substitution. Requires backside attack, leads to inversion of configuration.
Exactly. The nucleophile has to come in 180 degrees opposite to the leaving group. Now imagine an SN2 reaction on a cyclohexane ring.
Okay.
If the leaving group is in an axial position, where does the nucleophile need to attack from?
From the opposite side, so also along the axis, from the other face of the ring.
Right. And that line of attack is relatively unhindered. The nucleophile can come straight in, the reaction proceeds, and the new group ends up in the equatorial position due to the inversion.
Okay, seems straightforward. But what if the leaving group is equatorial?
Now think about backside attack. Where does the nucleophile have to approach from?
180 degrees away from the equatorial bond.
Yeah.
So kind of through the middle of the ring itself.
Exactly. And its path is directly blocked by the ring structure, specifically by the axial hydrogens, or carbons, on that same side of the ring. There's massive steric hindrance to the required backside attack trajectory.
So the reaction should be much slower.
Much, much slower. The source gives a fantastic example. For a particular system, substitution of an axial leaving group was 31 times faster than substitution of the corresponding equatorial leaving group.
31 times.
Oh.
That's huge.
Yeah.
So even if the equatorial conformer is way more stable and abundant,
Right, like 95% equatorial for a methyl group.
it might be the tiny amount of the axial conformer present at equilibrium that actually undergoes the reaction because the reaction pathway is so much faster from that conformation.
Precisely. The molecule has to flip to the less stable axial conformation first, and then it can react via SN2. The observed rate depends on both the equilibrium concentration of the reactive conformer and the rate of reaction from that conformer.
That completely changes how you have to think about reactivity. The most stable form isn't always the most reactive form.
It's a crucial lesson. And in extreme cases, like if you have a leaving group locked in an equatorial position in, say, a rigid transdecalan system where it cannot flip to become axial,
Then SN2 might just not happen.
it might not happen at all via that backside attack mechanism. The molecule might be forced into a different reaction pathway entirely, like an elimination reaction or maybe an SN1 reaction if possible, or it might just be unreactive under those conditions.
So conformational analysis isn't just about structure. It's directly predictive of chemical reactivity and reaction pathways. It explains why certain reactions work and others don't.
That's the power of it. It allows us to understand and predict chemical behavior based on three-dimensional shape and dynamics. It's fundamental.
So what does this all mean for you, listening in? Well, we've taken quite a deep dive into conformational analysis today. We've seen how these subtle twists and turns of molecules, from simple ethane all the way to complex steroids, really dictate their stability.
And, crucially, their reactivity.
Yeah. We saw how that chair conformation of cyclohexane is just this masterclass in avoiding strain, and how even a tiny difference, like whether a group is axial or equatorial, can have these massive implications for how fast a reaction happens, or even if it happens at all.
And understanding these 3D arrangements, these dynamic shapes, it's absolutely essential if you want to predict reaction outcomes or design new molecules, maybe for medicines or materials. It really helps you grasp the why behind so much of organic chemistry. It reminds us that structure isn't static. It's this constant dynamic interplay of forces.
It really makes you wonder, doesn't it? If a molecule's shape, just how it twists, can so profoundly influence its function, what other, maybe even more subtle architectural details are out there? What other hidden rules are governing the grand theater of chemistry and biology, just waiting for us to figure them out? Keep exploring, keep questioning, and keep delving deep.